So when we're doing optimization, I usually think of things in terms of some, like walking around some large valley. So the idea is that you're walking around this like large valley with different mountains and valleys and streams and stuff. And every point on this landscape corresponds to some setting of the parameters w. And you're this little guy who's walking around this valley. And you're trying to find, and the height of each of these points, is equal to the loss incurred by that setting of w. And now your job is, as this little man walking around this landscape, you need to somehow find the bottom of this valley. And this is kind of a hard problem in general. You might think like maybe I'm really smart and I can think really hard about the analytic properties of my loss function, my regularization, all that. Maybe I can just write down the minimizer. And that would sort of correspond to magically teleporting all the way to the bottom of this valley. But in practice, once your prediction function f and your loss function and your regularizer, once these things get big and complex and using neural networks, then you can't really hope, there's really not much hope in trying to write down an explicit analytic solution that takes you directly to the minima. So in practice, we tend to use various types of iterative methods, where we start with some solution and then gradually improve it over time. So kind of the very first sort of stupidest thing that you might imagine is random search. That will just take a bunch of w's sampled randomly and throw them into our loss function and see how well they do. So spoiler alert, like this is a really bad algorithm. You probably shouldn't use this. But at least it's kind of one thing you might imagine trying. And we can actually do this. We can actually try to train a linear classifier via random search for CFAR10. And for this, there's 10 classes, so random chance is 10%. And if we did some number of random trials, we eventually found, just through sheer dumb luck, some setting of w that got maybe 15% accuracy. So that's better than random, but state of the art is maybe 95%. So we've got a little bit of gap to close here. So again, like probably don't use this in practice, but you might imagine that this is something you could potentially do. So in practice, maybe a better strategy is actually using some of the local geometry of this landscape. So if you're this little guy who's walking around this landscape, maybe you can't see like directly the path down to the bottom of the valley, but what you can do is kind of feel with your foot and figure out what is the local geometry, like which way, if I'm standing right here, which way will take me a little bit downhill. So then you can kind of feel with your feet and feel where is the slope of the ground taking me down a little bit in this direction. And you can take a step in that direction. And then you'll go down a little bit, feel again with your feet to figure out which way is down, and then repeat over and over again and kind of hope that you'll end up at the bottom of the valley eventually. So this also seems like a relatively simple algorithm, but actually this one tends to work really well in practice if you kind of get all the details right. So this is generally the strategy that we'll follow when training these large neural networks and linear classifiers and other things. So then, like that was a little hand-wavy. So what is slope? If you remember back to your calculus class, then at least in one dimension, the slope is equal to the derivative of this function. So if we've got some one-dimensional function f that takes in a scalar x and then outputs the height of some curve, then we can compute the slope or derivative at any point by imagining, like, if we take a small step h in any direction, and then compare, like, what is the slope of that, take a small step h and compare the difference in the function value over that step, and then drive the step size to 0, that will give us the slope of that function at that point. And this generalizes quite naturally to multivariable functions as well. So in practice, our x is maybe not a scalar, but a whole vector of, because remember, x is something like right? So x might be a whole vector. So we need to generalize this notion to multivariable things. And the generalization that we use of the derivative in the multivariable setting is the gradient. So the gradient is a vector of partial derivatives. So the gradient will have the same shape as x, and each element of the gradient will tell us what is the slope of the function f if we move in that coordinate direction. And the gradient turns out to have these very nice properties, which is that so the gradient is now a vector of partial derivatives, but it points in the direction of greatest increase of the function. And correspondingly, if you look at the negative gradient direction, that gives you the direction of greatest decrease of the function. And more generally, if you want to know what is the slope of my landscape in any direction, then that's equal to the dot product of the gradient with a unit vector describing that direction. So this gradient is super important because it gives you this sort of linear first-order approximation to your function at your current point. So in practice, a lot of deep learning is about computing gradients of your functions and then using those gradients to iteratively update your parameter vector. So one kind of naive way that you might imagine actually evaluating this gradient on a computer is using the method of finite differences, kind of going back to the limit definition of the gradient. So here on the left, we imagine that our current w is this parameter vector that maybe gives us some current loss of maybe 1.25. And our goal is to compute the gradient dw, which will be a vector of the same shape as w. And each slot in that gradient will tell us how much will the loss change if we move a tiny infinitesimal amount in that coordinate direction. So one thing you might imagine is just computing this via finite differences. That we have our w. We might try to increment the first element of w by a small value h, and then recompute the loss using our loss function and our classifier and all that. And maybe in this setting, if we move a little bit in the first dimension, then our loss will decrease a little bit from 1.2534 to 1.25322. And then we can use this limit definition to come up with this finite differences approximation to the gradient in this first dimension. And now you can imagine repeating this procedure in the second dimension, where now we take the first dimension, set it back to the original value, and now increment the second direction by a small step, and again, recompute the loss, and use this finite differences approximation to compute an approximation to the gradient in the second slot. And now repeat this again for the third, and on and on and on. So this is actually a terrible idea because it's super slow. So you might imagine that computing this function f might actually be super slow if it's like a large convolutional neural network. And this parameter vector w probably will not have 10 entries like it does here. It might have like tens of millions or even hundreds of millions for some of these large, complex deep learning models. So in practice, you'll never want to compute your gradients via finite differences because you'd have to wait for like hundreds of millions potentially of function evaluations to get a single gradient. And that would be super slow and super bad. But thankfully, we don't have to do that. Hopefully you took a calculus course at some point in your lives. So you know that thanks to these guys, we can just write down the expression for our loss and then use the magical hammer of calculus to just write down an expression for what this gradient should be. And this will be way more efficient than trying to compute it analytically via finite differences. One, it'll be exact, and two, it'll be much faster since we just need to compute this single expression. So what this would look like is now if we go back to this picture of our current w, rather than sort of iterating over all the dimensions of w, we'll figure out ahead of time what is the analytic expression for the gradient, and then just write it down and go directly from the w and sort of compute the dw, or the gradient, in one step. And that will be much better in practice. So in summary, like this numerical gradient is something that's simple and kind of makes sense, but you won't really use it in practice. In practice, you'll always take an analytic gradient and use that when actually performing these gradient computations. However, one interesting note is that these numeric gradients are actually a very useful debugging tool. So say you've written some code and you wrote some code that computes the loss and the gradient of the loss, then how do you debug this thing? And how do you make sure that this analytic expression that you derived and wrote down in code is actually correct? So a really common debugging strategy for these things is to use the numeric gradient as sort of a unit test to make sure that your analytic gradient was correct. Again, because this is super slow and inexact, then when doing this numeric gradient checking, as it's called, you'll tend to scale down the parameter of the problem so that it actually runs in a reasonable amount of time. But this ends up being a super useful debugging strategy when you're writing your own gradient computations. So this is actually very commonly used in practice, and you'll do this on your assignments as well. So then once we know how to compute the gradient, then it leads us to this super simple algorithm that's like 3 lines, but turns out to be at the heart of how we train even these very biggest, most complex deep learning algorithms. And that's gradient descent. So gradient descent is first we initialize our w as some random thing. Then while true, we'll compute our loss and our gradient, and then we'll update our weights in the opposite of the gradient direction. because remember that the gradient was pointing in the direction of greatest increase of the function. So minus gradient points in the direction of greatest decrease. So we'll take a small step in the direction of minus gradient and just repeat this forever. And eventually your network will converge and you'll be very happy, hopefully. But this step size is actually a hyperparameter. And this tells us that every time we compute the gradient, how far do we step in that direction? And this step size, also sometimes called a learning rate, is probably one of the single most important hyperparameters that you need to set when you're actually training these things in practice. Actually, for me, when I'm training these things, trying to figure out this step size or this learning rate is the first hyperparameter that I always check. Things like model size or regularization strength, I kind of leave until a little bit later. And getting the learning rate or step size correct is the first thing that I try to set at the beginning. So kind of pictorially, what this looks like is that maybe we've got this. Here's a kind of simple example in 2 dimensions. So here we've got maybe this bowl, that's showing our loss function, where where this like red region in the center is this region of low loss that we want to get to, and these blue and green regions towards the edge are higher loss that we want to avoid. So now we're going to start off our W at some random point in the space, and then we'll compute the negative gradient direction, which will sort of hopefully point us in the direction of the minima eventually. And if we repeat this over and over again, we'll hopefully eventually get to the exact minima. And what this kind of looks like in practice is, oh man, we've got this mouse problem again. So what this looks like in practice is that if we repeat this thing over and over again, then we will start off at some point, and then eventually just taking tiny gradient steps each time, you'll see that the parameter will arc in towards the center, this region of minima. And that's really what you want, because you want to get to low loss. And by the way, as a bit of a teaser, we saw on the previous slide this example of like very simple gradient descent, where at every step we're just stepping in the direction of the gradient. But in practice, over the next couple lectures, we'll see that there are slightly fancier what are they called, these update rules, where you can take slightly fancier things to incorporate gradients across multiple time steps and stuff like that tend to work a little bit better in practice and are used much more commonly than this vanilla gradient descent when training these things in practice. And then as a bit of a preview, we can look at some of these slightly fancier methods on optimizing this same problem. So again, the black will be this same gradient computation, and these green, I forgot which color they are, but these 2 other curves are using slightly fancier update rules to decide exactly how to use the gradient information to make our next step. So one of these is gradient descent with momentum, and the other is this atom optimizer, and we'll see more details about those later in the course. But the idea is that we have this very basic algorithm called gradient descent, where we use the gradient at every time step to determine where to step next. And there exist different update rules which tell us how exactly do we use that gradient information. But it's all kind of the same basic algorithm of trying to go downhill at every time step. So here you can see on the left, we've got this problem where we're categorizing 3 different classes. And we've drawn the decision, and we've got these green, blue, and red points that are our training samples from these 3 classes. And now we've drawn the decision boundaries for these classes, which are the colored background regions, as well as these directions giving you the direction of increase for the class scores for each of these 3 classes. And now if you see, if you actually go and play with this thing online, you can see that we can go in and adjust the W's, and changing the values of the W's will cause these decision boundaries to rotate. If you change the biases, then the decision boundaries will not rotate, but will instead move side to side or up and down. Then we can actually make steps that are trying to update this loss. You can change the step size with this slider. You can hit this button to actually run the thing. So now with a big step size, we're running gradient descent right now, and these decision boundaries are flipping around and trying to fit the data. So it's kind of doing OK now, but then we can actually change the loss function in real time between these different SVM formulations and the different softmax. And you can see that as you flip between these different formulations of loss functions, it's kind of generally doing the same thing. Our decision regions are mostly in the same place, but exactly how they end up relative to each other and exactly what the trade-offs are between categorizing these different things changes a little bit. So I'd really encourage you to go online and play with this thing to try to get some intuition for what it actually looks like to try to train these linear classifiers via gradient descent. So now as an aside, I'd like to sort of talk about another idea, which is that of image features. So far we've talked about linear classifiers, which is just maybe taking our raw image pixels and then feeding the raw pixels themselves into our linear classifier. But as we kind of talked about in the last lecture, this is maybe not such a great thing to do because of things like multimodality and whatnot. So in practice, actually feeding raw pixel values into linear classifiers tends to not work so well. So it was actually kind of common before the dominance of deep neural networks was instead to have this two-stage approach, where first you would take your image and then compute various feature representations of that image that are maybe computing different kinds of quantities relating to the appearance of the image, and then concatenate these different feature vectors to give you some feature representation of the image. And now this feature representation of the image would be fed into a linear classifier rather than feeding the raw pixels themselves into the classifier. And kind of the motivation here is that there might be, so imagine we have a training data set on the left of these red points, and red points in the middle and blue points around that. And for this kind of data set, there's no way that we can draw a linear decision boundary to separate the red points from the blue points. And we kind of saw more examples of this in the last lecture. But if we use a clever feature transform, in this case transforming to polar coordinates, then now after we do the feature transform, then this kind of complex data set actually might become linearly separable and actually could be classified correctly by a linear classifier. And the whole trick here now is to kind of figure out what is the right feature transform that is sort of computing the right quantities for the problem that you care about. So like for images, maybe converting your pixels to polar coordinates doesn't make sense, but you actually can try to write down feature representations of images that might make sense and actually might help you out and might do better than putting in raw pixels into the classifier. So one example of this type of feature representation that's super simple is this idea of a color histogram. So you'll take maybe each pixel, you'll take this like hue color spectrum and divide it into buckets, and then for every pixel, you'll map it into one of those color buckets and then count up how many pixels fall into each of these different buckets. So this kind of tells you globally what kinds of colors are in the image. So maybe for this example of a frog, this feature vector would tell us that there's kind of a lot of green stuff and maybe not a lot of purple or red stuff. And this is kind of a simple feature vector that you might see in practice. Another kind of common feature vector that we saw before the rise of neural networks, or before the dominance of neural networks, was this histogram of oriented gradients. So remember from the first lecture that Hubel and Wiesel found that these oriented edges are really important in the human visual system. And this histogram of oriented gradients feature representation kind of tries to capture the same intuition and measure the local orientation of edges on the image. So what this thing is going to do is take our image and then divide it into these little 8x8 pixel regions. And then within each of those 8x8 pixel regions, we'll compute what is the dominant edge direction at each pixel, quantize those edge directions into several buckets, and then within each of those regions, compute a histogram over these different edge orientations. And now your full feature vector will be these different bucketed histograms of edge orientations across all the different 8x8 regions in the image. So this kind of gives you some, so this is in some sense dual to the color histogram classifier that we saw before. So a color histogram is kind of saying globally what colors exist in the image. And this is kind of saying overall what types of edge information exists in the image. And even localized like to different parts of the image, what types of edges exist in different regions. So maybe for this frog on the left, you can see he's sitting on a leaf, and these leaves have these dominant diagonal edges. And if you kind of visualize the histogram of oriented gradient features, then you can see that in this region, we've got kind of a lot of diagonal edges that this histogram of oriented gradient feature representation is capturing. So this was a super common feature representation and was used a lot for object recognition, actually not too long ago. Another feature representation that you might see kind of out there is this idea of bag of words. So here we've got this is kind of taking inspiration from natural language processing. So if you've got like a paragraph, then kind of a way that you might represent a paragraph by a feature vector is kind of counting up the occurrences of different words in that paragraph. So we want to kind of take that intuition and apply it to images in some way. But the problem is that there's no like really simple, straightforward analogy of words to images. So we need to define our own vocabulary of visual words. And now, so then we take this kind of two-stage approach, where first we'll get a bunch of images, sample a whole bunch of tiny random crops from those images, and then cluster them using something like k-means to come up with this, these like different cluster centers that are representing maybe different types of visual words in the images. So if you look at this example on the right here, this is kind of a real example of clustering actually different image patches from images. And you can see that after this clustering step, our visual words capture like these different colors, like red and blue and yellow, as well as these different types of oriented edges in different directions, which is kind of interesting that now we're starting to see these oriented edges kind of come out from the data in a data-driven way. And now once we've got these set of visual words, also called a codebook, then we can encode our image by trying to say, for each of these visual words, how much does this visual word occur in the image? And now this gives us, again, some slightly different information about what is the visual appearance of this image. And this was actually this is a type of feature representation that Feifei worked on when she was a grad student. So this is something that you saw in practice not too long ago. So then, kind of as a bit of a teaser, kind of tying this all back together, kind of the way that this image classification pipeline might have looked like, maybe about 5 to 10 years ago, would be that you would take your image and then compute these different feature representations of your image, things like bag of words or histogram of oriented gradients, concatenate a whole bunch of features together, and then feed these feature extractors down into some linear classifier. I'm simplifying a little bit. The pipelines were a little bit more complex than that, but this is kind of the general intuition. And then the idea here was that after you extracted these features, this feature extractor would be kind of a fixed block that would not be updated during training. And during training, you would only update the linear classifier that's working on top of features. And actually, I would argue that once we move to convolutional neural networks and these deep neural networks, it actually doesn't look that different. The only difference is that rather than sort of writing down the features ahead of time, we're going to learn the features directly from the data. So we'll take our raw pixels and feed them into this convolutional network, which will end up computing through many different layers some type of feature representation driven by the data. And then we'll actually train this entire weights for this entire network rather than just the weights of the linear classifier on top.
지난 시간에는 로스 펑션, 손실함수에 대해서 강의를 했는데 이번 시간에는 옵티마이제이션, 최적화를 통해서 로스 값을 어떻게 하면 줄일 수 있는지에 대해서 알아보도록 하겠습니다. 로스 값을 줄이는 문제는 종종 산비탈을 내려와서 가장 낮은 고도에 다다르는 것과 비유되기도 합니다. 우리는 로컬 그레디언트, 지역적인 경사를 따라서 계속 하강할 수는 있지만 그것이 반드시 가장 낮은 고도에 이르게 한다는 보장은 없습니다. 첫 번째 방법으로 랜덤 서치가 있습니다. 이는 발길 닿는 대로 가는 것으로 매우 나쁜 아이디어라고 할 수 있습니다. 랜덤 서치를 사용한 결과 테스트셋에서 15.5%의 정확도를 얻었습니다. 10개의 클래스가 있기 때문에 기대값이 10%인 걸 감안하면 그렇게까지 나쁘진 않은 스코어입니다. 가장 뛰어난 State of the Art 기법을 사용하면 95%에 다다를 수 있습니다. 두 번째 전략은 슬로프를 따라서 가는 것입니다. 물론 랜덤한 방법보다는 좋지만 로컬 미니멈에 갇힐 수도 있습니다. 원 디멘전에서 함수의 데리버티브는 다음과 같이 표현할 수 있습니다. 멀티플 디멘전에서는 그레디언트는 각각의 디멘전에 대한 벡터로 표시할 수 있습니다. 각 디렉션의 경사는 디렉션과 그레디언트의 덧 프로덕트로 표현할 수 있습니다. 여기서 하강 경사가 가장 큰 방향을 네거티브 그레디언트라고 합니다. 실제 예를 통해서 계산을 해보도록 하겠습니다. current W 값에서 현재 로스 값이 1.25347입니다. 첫 번째 디멘전에 그레디언트를 적용한 결과 로스 값이 1.25322로 미세하게 감소한 것을 알 수 있습니다. 이에 대해서 그레디언트 DW 값을 계산하면 마이너스 2.5를 얻을 수 있습니다. 이를 차례로 적용하면 그레디언트 DW의 두 번째 값인 0.6을 얻을 수 있습니다. 이러한 방법은 어리석고 비효율적입니다. 로스는 W의 함수이기 때문에 우리가 원하는 것은 그레디언트 L입니다. 우리는 캘큘러스를 사용해서 애널리틱 그레디언트 값을 구할 수 있습니다. 요약하면 뉴메리컬 그레디언트는 approximate, 근사값이고 느리고 반면에 쉽게 쓸 수 있습니다. analytic gradient는 exact하고 빠르지만 에러 프론합니다. 즉 에러가 발생할 수 있습니다. 실제로는 analytic gradient를 사용합니다. 그러나 implementation을 numerical gradient로 체크하는 것이 좋습니다. 이것을 gradient 체크라고 합니다. 간단한 vanilla gradient descent는 다음과 같이 쉽게 implementation 할 수 있습니다. 이 그래프에서 하얀 점은 original W이고 하얀 화살표는 negative gradient direction입니다. 파란색에서 빨간색으로 갈수록 옵티마이제이션 포인트에 다다르는 것입니다. 바닐라 그레디언트 디센트의 시뮬레이션입니다. 알고리즘에 따라서 다른 시뮬레이션 결과가 나올 수도 있습니다. 지금까지는 이미지 데이터에 RGB 데이터를 바로 리니어 클래시파이어로 분류하는 것에 대해서 배웠습니다. 이번에는 이미지 데이터에서 어떤 피처들을 익스트랙트 한 뒤 그것을 리니어 클래시파이어에 적용하는 것에 대해서 알아보도록 하겠습니다. 이미지 피처에 대한 모티베이션을 보면 왼쪽의 그림을 보면 빨간 점들과 파란 점들은 리니어 클래시파이어로 분류하기가 어렵습니다. 그런데 만일 우리가 거리 r과 각도 θ의 피처를 xy로부터 익스트랙트 할 수 있다면 오른쪽 그림에 나타난 바와 같이 빨간 점과 파란 점들을 리니어 클래시파이어로 쉽게 분류할 수 있습니다. 문제는 이러한 피처 익스트랙션이 도메인과 데이터에 따라서 다를 수 있기 때문에 어떻게 피처 익스트랙션을 할 것인가가 어려운 문제입니다. 한 가지 방법은 컬러의 피처를 익스트랙션 하는 것입니다. 그러나 이 방법은 같은 개구리에 대해서도 조명에 따라서 컬러 값이 달라지고 또 백그라운드에 따라서도 달라지기 때문에 한계를 갖고 있습니다. 또 다른 방법은 Histogram of Oriented Gradients HOG입니다. 왼쪽 개구리에서 엣지 디텍션을 하여서 그 엣지의 방향을 벡터로 나타냅니다. 그러나 이 방법은 카메라나 오브젝트의 트랜스포메이션이나 디포메이션을 다루기 어렵다는 문제점을 가지고 있습니다. 이미지의 피처를 익스트랙션 하기 위해서 내추럴 랭귀지의 back of words 방법을 사용할 수도 있습니다. 1단계로 문장에서 월드에 해당되는 이미지의 코드북을 만들도록 합니다. 2단계에서는 이러한 이미지들을 인코딩 합니다. 그러나 이 방법은 이러한 코드북을 만드는 것이 쉽지 않다는 문제점을 갖고 있습니다. 이렇게 이미지 피처를 익스트랙션 하는 방법은 컨볼루셔널 뉴럴 네트워크가 활성화되기 전까지 주로 연구되었습니다. 현재는 컨볼루셔널 뉴럴 네트워크의 전 단계가 피처 익스트랙션의 역할을 하고 있고 데이터를 통한 트레이닝을 통해서 피처 익스트랙션이 수행되고 있습니다.